my name is Kelly Marchisio, and today I'll be presenting our work entitled IsoVec, Controlling the Relative Isomorphism of Word Embedding Spaces. This is joint work with my co-authors at Johns Hopkins University that was presented at EMNLP 2022. To get on the same page about terminology, we'll talk about embeddings. In NLP, an embedding is a vector representation of a word, subword, or phrase. In word embeddings, words with similar meaning should have similar vectors. So if you look at this English embedding space here, we'll see that numerically, it appears as though fox and dog have similar vectors. And then if we can imagine these as living in some high-dimensional Euclidean space, it should be the case that words with similar meanings are close to each other in that space. So we can see that dog and fox are near each other in the shared space, in the high-dimensional space. A recurring theme in this paper is bilingual lexicon induction. The problem statement here is given a data source. We want to induce a dictionary of words and their translations. So if we have a list of words in blue in English on the left here, the goal is to find the associated translations, for instance, in French on the right. Bilingual lexicon induction from word embedding spaces typically begins with two embedding spaces that were trained separately on monolingual data. So on the left here, we have an English embedding space, and then on the right, we have a French embedding space. We can assume that a list of seed translation pairs is given. We can sort the corresponding submatrices of the two embedding spaces such that each row in the sorted matrix corresponds to the seeds that we've been given. And then the task is to find the translations for the rest of the words in the spaces. We can think about this geometrically. So imagine that we have this blue English space and a separately trained French embedding space in red. The goal is to figure out how to get these to live in a shared space such that words that are translations of one another live next to each other in the space. For instance, we can see that brown and its translation brun in French are near each other in this joint embedding space. So how might you create this shared cross-lingual embedding space? One possible way is to use linear transformations only to try to optimally map these one onto the other. We'll recall that linear transformations are reflections, rotations, and dilations. So imagine that we take this blue English space on the left, and then imagine we reflect it. And here we can see that the words that are translations of one another still are not well aligned, but then we can rotate the blue space, and now it looks like the translations are near each other in the space. But what we know from the literature is that the ability to map word embedding spaces to a shared space depends critically on their geometric similarity. So imagine if the English word embedding space had looked like this, like we see in blue. Now we'll see that no matter the rotation, the dilation, or reflection, we cannot seem to line these up well. And that's because these two spaces are geometrically dissimilar, so they cannot be mapped one onto the other with linear transformation alone. Another word for geometrically similar that's used in the NLP literature is isomorphic. I'll say that this is different than the definition that you see in mathematics, which is a rigorous definition with a specific meaning. But in NLP, we soften the definition of isomorphic considerably, to the fact that we can talk about degrees of isomorphism or isomorphism on a scale. So you might have that embedding space 1 is more isomorphic to embedding space 2 than it is to embedding space 3. So the way that this problem was talked about in the literature is that certain embedding spaces are non-isomorphic, whether because one comes from a low resource language and the two languages are dissimilar, or whether one is in a different domain. And the way that the literature had talked about this was these embedding spaces are non-isomorphic, they're not going to map well, isn't that sad? But the idea in this paper was, well, why do we have to restrict ourselves to the geometry that an embedding algorithm naturally produces? So I thought, why not introduce metrics of isomorphism into the embedding training itself? try to train embeddings to be more geometrically similar to one another, and then we won't really have a problem in mapping them via linear transformation in our downstream tasks. So in IsoVec, we address the root cause of faulty cross-lingual mapping. That's that separately trained word embedding spaces are non-isomorphic, and we do this by upping the geometric similarity of the spaces during training. For background, there are many ways of measuring geometric similarity. One way might be to take the pairwise cosine similarities of words in space X. Similarly, take the pairwise cosine similarities in space Y, correlate these, and this is called relational similarity, and this exists in the literature. Here's another way. So imagine that your source words are the little blue dots and your target words are the little red dots. We want to find the nearest neighbor of each blue dot in the red space. And we can see that here these two blue dots shared the same nearest neighbor, and it was distance 2 away from it. We then go from the red to the blue space and find the nearest neighbors in that direction. So we can see that this relationship was not symmetric. It's not necessarily the case that nearest neighbors in one direction are the nearest neighbor in the other direction. So here we can see that this red dot over here, its nearest neighbor was 3 away. The worst case over all these distances is called the Hausdorff distance, and that's 3. But also we'll note that it is potentially possible to rotate one of the spaces to make these numbers a little bit smaller. So imagine that you rotate the red space, and we can see that now we've reduced the distance from the red points to their closest nearest neighbors. Now the worst case distance between this optimally orthogonally transformed target space and the source space is now 2. So this is the worst case nearest neighbor after best orthogonal transformation. This is called Gromov-Hausdorff distance. So our goal in this paper is going to be to train word embedding space X such that it captures distributional information as we would like it to when creating word embeddings, but that it is also geometrically similar to a reference space Y. In other words, an entire literature tried to find or learn a mapping to induce accurate translation dictionaries, but no one tried to make the embeddings themselves more mappable until we did. As a little reminder, our goal is this, to have two spaces that are geometrically similar enough that they can be mapped to a shared space. What we do not want to see is a geometry like this. So this one wouldn't map nicely into this shared space. So concretely, we start with your standard skip-gram loss, which you'll be familiar with from Word2Vec. We will then add in an isomorphism loss, which is calculated in reference to a fixed embedding space that was trained previously. These fixed embedding spaces ideally would be high resource and expected to have a nice geometry. And that's because hopefully we would have had enough data to train that reference embedding space such that it itself has a nice geometry. And then the goal is to train the low resource embedding space with the IsoVec loss such that we are encouraging the source embedding space to have a similar geometry to this target embedding space that we know is pretty good. So imagine that our fixed reference embedding space looked like this in blue. Without IsoVec, maybe you'd induce this geometry. And with IsoVec, our goal would be to induce a better geometry. In the IsoVec paper, we explore 3 different isomorphism losses, 3 supervised and 2 unsupervised. So let's jump straight into the results. In our baseline experiments, we do the standard method of training 2 word embedding spaces separately using the same training algorithm, and then we map them using a tool called VecMap in unsupervised mode. VecMap is essentially iteratively applying what's called the Procrustes solution, which is the optimal orthogonal transform. In this case, it's unsupervised, but it repeatedly applies that to try to get the best transform possible. And in the main experiments without IsoVec, we can see that our precision for Ukrainian English is 12.6. With IsoVec, it improves a bit to 14.0. But now I'm going to show you where IsoVec really has strengths, and that's when we have algorithm or domain mismatch between the source and target spaces. So it's a well-known phenomenon that if you have two embedding spaces that were trained with different algorithms, then they are going to have different underlying geometries and not mapped nicely via linear transformation to a shared space. So in this case, the algorithms that we used aren't even that different. We use the Word2Vec that you pull straight off GitHub, the official release on the source side. We then use my implementation of Word2Vec, which I made in the course of writing the code for IsoVec. It is essentially doing the same thing as Word2Vec, but it's put on GPU, and we'll see what the effects are of that. So when we do these two slightly different algorithms on source and target side, without IsoVec, our performance drops severely to 4.4%. With IsoVec, we recover almost the entire full performance, and we achieve a 13.4% accuracy. Now we'll look at domain mismatch, which is a very difficult condition in unsupervised mapping. Here you have one domain, say the news domain on the source side, and a different domain, for instance, web crawl on the target side. And we know from the literature that this makes embedding space mapping really difficult. And indeed, in our baseline experiments, this causes performance to drop down to 0. But now if we add in IsoVec, we achieve 13.1%, which is recovering almost all of the performance of using IsoVec initially, and indeed it's even stronger than the baseline domain-matched experiments without IsoVec. We run these experiments on Bengali English and Tamil English, and we see similar results across those. So that was IsoVec. Thank you for your attention. You can try this. It is available at github.com/kellymarquisio/IsoVec. Thank you.